In this video we're going to look at how to process a depth profile that was collected using a Thermo CasaXPS instrument. The data are saved as binary files within a directory structure, and the Avantage system includes another program called dataspace_batch_dump that converts the binary files into an ASCII equivalent. And once the data are in these ASCII equivalent data files, CasaXPS can convert these .avg files into a VAMAS format. And the whole process is performed using the Convert to VAMAS File dialog window. And this allows you to reverse the directory structure to the point where these files can be converted. In this case we've got a top level directory, and this corresponds to this directory we see here. And within it is another directory, and that directory includes a folder that contains the .avg files. So if I look inside this folder, you can see there's an Oxygen 1S scan and a Silicon 2P scan, and they both have the file extension .avg. So these are now in an ASCII format that we can convert. And in order to do that, if we go to the directory level where the data folder containing the .avg files resides, and then we type in .dvg, and this is a filter that when open is pressed or return is pressed, then the current directory is searched for data folders, and as many data folders as are within the directory, there will be that number of VAMAS files created by this filter. In this instance we've only got the one folder, so when I press open, only a single VAMAS file will be created. So the search has been performed and it's found the one directory, and if I say yes to continue, the data within the AVG files in that directory are converted into the profile in a VAMAS format, and it tells me that I've just created one new VAMAS file. To verify that the data conversion occurred and a VAMAS file was created, if we look at the Convert to VAMAS File dialog window, we see there's a new file that resides in the same directory as the data directory that contained the .avg files. And the new VAMAS file has been assigned the name for the data directory, and within the VAMAS file all the spectra that were within the AVG files are collected and organized according to an experimental variable. So we had two files. One was the .avg file corresponding to Oxygen 1S, and the other one was AVG files corresponding to Silicon 2P. So these have all been loaded and ordered according to the etch time for the sputter depth profile. The particular sample that we're looking at is a silicon dioxide layer on silicon, and the idea is to etch through the oxide layer and expose the silicon, and therefore calculate the depth of the oxide layer on the silicon. And in order to do this we need to calculate the point within this profile at which the oxygen disappears, and also we need to make sure that it corresponds with the position at which the silicon dioxide disappears when calculated from the Silicon 2P. That is because there is chemical state shifts within the silicon that allow us to see the difference between a silicon oxide and an elemental silicon peak. So if we can trace these intensities as a function of the sputter time, and then calculate a sputter rate so that we can convert sputter time into depth, we will be able to identify the point in terms of nanometers at which the oxide layer has been removed by this process of sputtering with an ion beam. To create a depth profile from a set of spectra that are measured by XPS, we need to do the standard techniques for quantification. That is to say, for each one of these spectra we need to define a quantification region, and this will allow us to identify intensity that can be scaled by various correction factors such as the relative sensitivity factors that will give us the amount of substance for this oxygen. So I've just created a region on one of these oxygen peaks, and if I propagate this region to the other oxygen peaks, then in terms of this oxygen that's sufficient to work out the amount of oxygen because there's no real chemical state here. On the other hand, if we look at the silicon, then create a region and perform the same operation, propagating the region, we have signal above background, but this signal is divided into the silicon that is bonded to oxygen and elemental silicon, and then at the interface we have a combination of both oxide and elemental signal. And the idea, if we're going to do a good job of creating a depth profile, is that we would like to separate the signal from the oxide and the elemental form and plot these as a function of the etch time along with the oxygen signal. To do a full analysis of this profile, we would need to do an analysis of the silicon signal to divide it into the oxide and the elemental form. However, using regions where we simply look at the signal from the silicon as a whole and then the oxygen as a whole, we can profile this using options on the report spec property page. So I've selected all of the VAMAS blocks in the right hand side, and then I'm going to use the custom report, and the custom report lists all of the quantification items. That means regions or components that are defined on these selected VAMAS blocks, and you can see here that the names for the regions are oxygen 1s and silicon 2p. So these indicate what's available to create a report, and then using these buttons we can form quantification reports in this table here that represents the traces that we're going to create and the way we want to combine signal from regions and components to form these traces. Now in this case they're very simple, they're just regions, so I'm selecting the regions button, so any name that is associated with a region is copied through to this table, and the table indicates the name of the trace. So each one of these traces will be named oxygen 1s and silicon 2p, so we should have two traces, and the formulae that are used are simply the names themselves. So this is a very basic formula, although it could be any combination of silicon, oxygen, or any components that are defined on these data. But given that we've just got regions here, the next step to create a profile is to press the area report, and this will act on all of the selected VAMAS blocks. So when I press area report, I then get a text table where we have a set of columns that are calculated from the regions on the data that was selected in the right hand side. So we have the etch time, the oxygen as measured in counts per second EV after scaling for relative sensitivity, escape depth and transmission, and similarly counts per second report for the silicon, and then from these values atomic concentrations are calculated, which are reported as a percentage for the oxygen and the silicon. And if we want to see what this looks like visually, on the file menu there's an option that says create profile, and we end up with a new VAMAS file that contains 4 VAMAS blocks, one for each of the columns that are plotted as a function of the first column, which was in this case the etch time. So observing as a percentage the oxygen and the silicon, you can see how that you have a level oxygen signal up to a point, and then the oxygen reduces, and at the same time the silicon signal increases, and this represents the range of a material where we have an overlayer of silicon oxide, and then it enters the silicon in elemental form. We can also plot the signal as measured by the peak areas, and when we do this you can see how the oxygen follows a trend which is mostly level, and then the signal drops off dramatically as we go into elemental silicon as expected. But when measuring the silicon, you see that the silicon is a signal that is calculated within the oxide which is slightly less than the silicon when calculated outside of the oxide. If we wish to calculate a sputter rate from the data itself, and we can do this using an equation known as the Hill equation, what we need to know is the intensity for silicon in the silicon oxide, and we need to know the intensity for silicon in the elemental silicon. And if we have these two pieces of information, then the Hill equation will allow us to estimate a film thickness at some point within this profile where we see both elemental silicon and silicon oxide. So hopefully somewhere in this region here there will be a spectrum from which we can estimate an overlayer thickness using the Hill equation. The idea behind calibrating the etch time to depth in nanometers is to make use of the Hill equation, as stated earlier. And the concept of the Hill equation is based on that electrons that move through a solid state are attenuated using an exponential model, where the exponential model defines the rate at which intensity decays as a function of the depth. And in this case, a profile is removing the oxide layer. And while we're within the oxide layer, we have effectively got a bulk oxide material, and it's producing a spectrum that looks very much like this one here. And when we approach the interface between the oxide and the substrate, the fact that XPS samples a film in its own right of about 10 nanometers at the energy of these electrons, then we're looking deeper into the sample than the actual layer that has been uncovered by the depth profile. And under this circumstance, we would expect to see a peak that represents the oxide peak and some evidence of an elemental peak. And the scenario is that we have a small amount of the silicon and a film of oxide that we can measure using the Hill equation, and that gives us an idea of the sputter rate, because the profile will continue and eventually will remove all the oxide, leaving just the elemental silicon. So we should get an idea of how long it takes in seconds to remove the oxide layer of a given thickness, and hence calculate a sputter rate. Now what we need to do this is a pair of intensities that are calculated for silicon in an oxide state. That's one here is the oxide, the overlayer, and silicon in the substrate state. So I've illustrated here as if we've got bulk oxide and bulk silicon, and we need to calculate these areas because the ratio of these two areas is not unity, as was illustrated by the profile, and these are used to scale the intensities that we calculate for the oxide layer on the elemental silicon, and this provides the means by which the scaled intensities are then converted to a depth scale using the effective attenuation length for silicon dioxide. We therefore need to calculate 4 quantities from the data set. We need a spectrum that represents bulk oxide, bulk silicon, and then the interface region that should provide 2 intensities. When combining the Hill equation will give us the depth of the overlayer. So if we go back to the data set, we should identify peaks that are representative of the bulk oxide, and let's try one here that is representative of the bulk silicon, and this one represents a combination of both. So we have an oxide layer and we have an elemental signal, and these 2 peaks from a single spectrum, when fitted using appropriate synthetic components, will provide 2 pieces of information, whereas the oxide and the elemental spectra will provide the other 2 pieces of information that are required for the Hill equation. To calculate this sputter rate, I will copy these to a new file. And as it stands, these all have the same element transition fields because they're all silicon 2p, but this one represents an oxide. So what I'll do is I'll change the element transition and I'll call this ox for oxide, and similarly I will say this is the interface, and finally we'll set this one as the elemental form of the silicon. So using the edit mode, although originally they had different etch times and therefore they would appear on different rows, if I use edit mode they all have the same sample identifier, and therefore I have the spectra all on the same row, which is what is required when you use a quantification report generated from the report spec property page. Now that I've identified the different silicon peaks of interest, what we'll do is construct a peak model, and we'll do this using a background and a pair of components for the elemental peak, and we ought to have a pair of components for the oxide also. Let's just add some peaks here. This is using the Quantification Parameters dialog window and the Components Property page. So I've placed 2 peaks here. They're my initial positions for the peaks, and I would like to have a pair of peaks similarly located for the elemental peak. So let's copy all of these peaks and we'll say paste, and then I'm going to hold the control key down so I can move my newly created peaks over here. And if I say fit, I end up with a rather poor fit and nowhere near the type of fit that I'd like for these peaks. So I'll recall what I started with, and let's enter some constraints. So I'm going to say A star 0.5. This is approximating the relationship between the 3/2 and the 1/2 peak of silicon in a 2-piece state. So I need to do the same thing for the 2 peaks that I've got for the elemental form. Now if I say fit, I'm getting closer, but it's not really the type of fit that I'd feel comfortable with. So let's put in a few more constraints. In this case, let's say that we'd like the forward half maximum for these 2 peaks to be the same, and we'll do the same for the silicon elemental peaks. So I enter C star 1 and then say fit. Well, the elemental peaks have produced something that's a little bit more meaningful. The oxide not so good, so let's change the line shape and make all of these line shapes the same as 1.2 in the LA line shape. This is producing more of a Lorentzian shape, and when I say fit, I start to get a similar sort of offset here between these oxide peaks that I have for the elemental peaks. So that's slightly better, but I'll do one further step. I'm going to put in a min limit background type, and what this has done is it's basically put in a flat background beneath both of these peaks, and I'm doing this because I believe there should be no rise in the background associated with these oxide peaks, whereas I believe the rise should occur in relationship with these elemental peaks for the silicon. And so to account for such a rise, I'm going to introduce another component, and I'm going to call this component SB open bracket 0 close bracket, and then it follows with a line shape. And what I'll do is I will use the same line shape everywhere, and it updated the line shape without updating SB. SB stands for Shirley background, and it's being calculated from the line shape that's specified here. Let me just give it a little bit more room in terms of area, because backgrounds are relatively intense items, and if I say fit here, I end up with a step now that is occurring at a point just after the elemental peaks. The offset between these elemental peaks should be reproduced to some extent between these oxide peaks. Let's just investigate the offsets. So if I type in A and press return, this tells me that the current offset between these oxide peaks is 0.176. Now if I go to the elemental peaks and do the same, this time I type C and press return, the D peak is offset from the C peak by 0.609. So what I'll do is I'll take this offset and I'll apply that to the oxide peaks. The oxide peaks are very highly correlated, and there's not much useful position information within these peaks. So provided I have a good fit and the elemental and the oxide peaks are of similar offset, then this will represent a peak model that should be able to extract information about the oxide and the elemental signal. The custom report makes use of information that's gathered by names on the components and the regions. So before we go too much further, let's identify one of these as being the region. So I'm giving it a different name. I'm adding an R. So every time I see the name silicon 2PR, I know it's from a region. when I go to the components, these are oxides, so although this is from the interface originally, I'm going to say oxide. And similarly, I want to specify the second peak with the same name. And the reason I give it the same name is that intensities are gathered based on the name. So if I give the same name to two components, when I create a report using the custom report, then both of those peaks would contribute to the oxide peak. Now the one thing that I need to just verify, although it won't be important for the Hill equation, provided that I use the same RSF everywhere, then I can go through and assign the RSF that is for silicon 2P in this case. Now let's look at the silicon 2P elemental peak, and I'm going to give again the same RSF and a different name from the oxide, so I can differentiate the elemental signal from these components. Same RSF, so I can differentiate the signal from the elemental peaks and the oxide peaks by name in the custom report. And I have a background. This is my background signal, and I do not want to have the background included in the result, so I'm going to set that RSF to 0. So now I have a set of peaks. They have relative sensitivities assigned, they have different names for the oxide and the elemental peaks, and I've set an RSF of 0 for the background peak. So the next step will be to see how well this peak model applies to these two spectra that are either from the oxide or from the elemental part of the depth profile without any interface relationship, and so we should have a pure oxide in one case and pure elemental in the other case. We'll test this peak model against these other two spectra, and I'll do this by propagating from the interface spectrum to these two bulk type spectra. So I right click over the spectrum, I'm going to propagate regions, components. I'm not going to auto fit because not all of these components should fit well to these data. There should be two peaks from this component model that will apply to the oxide and two that will apply to the elemental. So rather than fitting, I'm going to wait and have a look at the result of copying these into the data. They're from different element transitions, so I need to say yes to this, and then I can have a look and see. So if I turn off these components, you can see that there's the oxide peak. Put the components on, so these elemental peaks are not part of this peak model. So before I go too far with this, what I will do is I will constrain the peaks, in this case from the elemental case, to be within a certain range. So I've set hash 0.4. This will prevent these peaks from moving too far when the fit is performed. And that's because I'm expecting these to go to 0. And as we see, they do go to 0, and they are up against the limits of the constraints because they've turned red when viewed here. So now we've got a fit that will provide an estimate for the oxide. Let's have a look at the elemental form. Once again, I've got additional peaks that are not required. These ones are the oxide, this is the elemental peak. I've got elemental peaks here. So again, I will limit the oxide peaks to be within a certain range by saying hash 0.4. This will take the current value and introduce constraints that will limit the current value by plus or minus a value of 0.4. I'm now going to say fit, and we end up with a fit that involves the two component peaks from the elemental form. It's also got the step that is associated with the silicon elemental rise in the background, and once again it's indicating that this step occurs offset from the peaks themselves. So this is consistent with a semiconductor. And so we can now estimate the bulk silicon intensity based on this peak model. I need to make use of these intensities within a custom report. So I'm going to refer to this as bulk oxide that is not there. So I'm going to call that 0. I'll copy that and paste it here. This is so that I can identify the origin of signal. Now, although these are very small, I want to remove them from the calculation and only make use of the elemental bulk from the elemental data. Again, I will give these the same name, so I'm copying and pasting here. The background has the name, but it also has a 0 offset, so that's not a problem. Now if I go to the oxide spectra, I've got here, this is not the interface, but this is bulk. So I'm going to specify the name oxide with a bulk. In this case, I think we'll just call these 0 for the elemental peaks, because these are not part of the calculation. They should have gone to 0, they have gone to 0, but just to be sure, I'm giving them a different name so I know exactly where they're coming from when I process these data using the custom report. Now I've got peaks here that are oxide and elemental, and these are the interface oxide and elemental peaks. This is the bulk for the oxide, this is the bulk for the elemental, and what I can do is create a custom report that will involve a Hill equation so I can calculate the thickness that is associated with this interface where we've got both oxide and metal. So I've now prepared all of these spectra with the appropriate names in the components in order to do a Hill calculation. And to see the names that are available to me, I'll select all of these VAMAS blocks, and then we can see there's a background, we don't want that. The elemental, that's part of the interface. We've got a bulk elemental, and we've also got a bulk oxide, and this is the interface oxide. So it's a question of now defining a formula that's appropriate out of these names. So let's click where it says name, and it gives us a new entry, and I'll call the quantity that I'm calculating the depth. And now I have to introduce a formula. So the formula includes the effective attenuation length, and we'll estimate that as 3.25, and that's based on Martin Sears universal formula for the effective attenuation length. And then I need to say log, this is the natural log of 1 plus, and then I have to have a ratio of the bulk, and I need to multiply that by a ratio of the interface intensities, and this will be performed by entering the appropriate names from the list here. So I need first of all the silicon 2p, and I need the substrate, so that's elemental bulk was the name, and I need to divide that by the silicon 2p oxide bulk. It's very important that I use exactly the same name that the components are named with. So that represents my scaling, and then I need to have the intensity from the overlayer, which is the oxide, and I need to divide that by the intensity from the substrate, which is the elemental. So these hopefully are now the same names that I used for the 3 different spectra that have components fitted with the appropriate components set up so that we can calculate from this equation here, which is a definition of the Hill equation, assuming a normal takeoff angle. If it was not a normal takeoff angle, then there's a cosine theta involved, but since it's 90 degrees, that is 1, so I'm just entering the effective attenuation length and then the scaling factors that determine the relative intensity of signal measured from bulk elemental and bulk oxide. And then I've calculated from the peak model that was on the interface spectrum the ratio of the oxide peaks to the elemental peaks, and put together this should now calculate in nanometers the depth of the oxide over the silicon at that point in the depth profile. So when I press OK, I see the expression defined here that I've just entered on the dialog window. I've got all of these selected in the right hand side because these are the source for the information that will be gathered and used in this calculation, and then I can say area report. And we just observe that we've got 8.4 nanometers of oxide at that particular point in the depth profile. The film thickness allows us to calculate the sputter rate, and if I just take a copy of the quantity that I've just calculated and then go to the profile, it was at this point that the interface was calculated, the film thickness, and at about this point you can see that mostly the oxygen's gone away. So in an interval of about 120 seconds, 8.4 nanometers was removed by the etching. So we can calculate this. If we want to, we could use this or a calculator. So I say that the 8.4 nanometers is removed in 120 seconds of etching, and that gives me an etch rate of about 0.07. So having calculated an etch rate of 0.07 nanometers per second, we can go back to the original data, and we have currently an etch time here, and we want to convert this to depth. So if we select all of these VAMAS blocks, and then there's an option here that lets you enter an etch rate, so 0.07, and this will be depths in nanometers. And when I press apply, we end up with an experimental variable that is now in nanometers. So if I create the profile again based on these regions and then create the plot, at this point here we can see that the interface is now indicating that we've got a change from oxide to elemental silicon, and it's at about 75 nanometers. So the oxide layer is about 75 nanometers thick. We should say at this point that the etch rate was calculated using a number of assumptions, such as the universal calculation of an effective attenuation length, that the crater bottom was flat, and that the elemental silicon was sufficient to do a hill calculation. There are lots of places where this calculation could have been in error, but nevertheless it illustrates how a peak model could be used to work out an etch rate for a depth profile and estimate the depth of silicon oxide on silicon.